Okay, so I wanted to dive a little bit deeper into what this isoelectric point is. So we said that isoelectric is where um, the pH at which the amino alcohol has an overall neutral charge. So let's see what happens when the pH is higher or lower than that isoelectric point. We're also going to define this. I wrote earlier in the notes IEP as an electric point, but the better way to write this is P with a capital I, lowercase p, capital I. So point of isoelectric. So amino acids in acidic solution. So if the pH of the solution, let's do a new color. If the pH is lower, less than the isoelectric point, you're going to have positive ions. Okay, so a neutral amino acid, so alanine here is neutral. It has a positive charge and a negative charge. If I then put it in acid, we then have a positive 1 overall charge associated to our molecule. So this negative charge is going to steal one of the hydrogens from our acid. So we have a neutral amino acid. If it's in acidic solution, the amino acid is going to become acidic. It's going to become a +1 charge and then have your neutral water left over. In a basic solution, it'll be the opposite. So in this acidic solution, the carboxylate was what was protonated. But now in a basic solution, where your pH is greater than the isoelectric point, you make, well, we got to adjust this a little bit, don't we? Let's just erase where we write charge. We're going to have +1. The overall charge is +1. So in a basic solution, we have pH is greater than isoelectric point. Then we're going to have negative ions. So we're going to have overall negative charge, not neutral. So we have our neutral amino acid again. We have our base that equilibrates, and it's going to deprotonate this ammonium. So now it's neutral. We're left over with a -1 charge. Okay, so the acidic and basic amino acids are going to be a little bit weird in their isoelectric point. So make sure you're looking at your chart to look at where that isoelectric point is so that you can appropriately protonate and deprotonate the molecules. So let's practice this a little bit. Asparagine has an isoelectric point of 5.4. Match the following structures of asparagine to the pH values where they would occur. So what we're looking for is the charges. So what I like to do is to highlight the different charges associated. So this first one, we have a charge, a carboxylate. However, the amine side is neutral. This one in the middle, we have charges on both sides. We have a positive charge and a negative charge. And then on this one, we have a positive charge. So let's see what that means. So where our molecule is overall neutral is our isoelectric point by definition. So this in the middle is going to be our isoelectric point because our net charge is 0. So the pH equals isoelectric point, which equals 5.4 in this case, because we're told that in the question. Okay, so now we need to figure out which one is in a basic solution and which one's in acidic solution. So if our overall net charge, so let's look at the first molecule. The overall net charge is -1. So that means if we have a negative charge, we have to be in a basic environment. You cannot have an acid with something with a negative charge because those are going to neutralize one another. So if the net charge is -1, we're in a basic environment. So pH is greater than Pi. So the pH is going to be, based off of our choices, it's going to be 10.2. So number 3. Okay, and then our last one, we're going to look at our overall net charge. So we highlighted them all. We have one charge in the molecule and it's +1. So that means we're in an acidic environment. We have a positive charge overall. So pH is less than Pi. So that means we have to have 2.1 as our pH. So this is going to be a pH match with number 1. Okay, so take a moment and try the second one with proline on your own, and I'll go through the answer with you as well. So again, let's highlight each of the different charges. So we have a positive charge and a negative charge on the first one. We have a negative charge on the second, positive charge on the third. Oh, I'm sorry. Okay, so looking at this, our overall net charge, let's just go ahead and write them for all. So this first one, the net charge is neutral, so it's net charge of 0. Second one is net charge is -1. Third one, net charge is +1. So let's define what this means. When the net charge is neutral, net charge is 0, that means the pH is equal to the Pi, which then is whatever it says in your chart or in the question in this case. So that means it's 6.3, which is number 2. So I'm going to mark it as number 2. In the middle molecule, we have a basic environment because we have a negative charge associated with our molecule. So pH is greater than Pi. So then we would have our 11.2 pH, which is number 3. And then our last one, we have a positive charge, which means we have an acidic solution. So pH is less than Pi. pH of 1.8 is what our option is. So that's number 1. Okay, so where these start to get really tricky is when you have charged species as well. So if you have a charged species, it's going to be a little bit different. We'll practice that in our practice problems as well.